We will do some more applications of Amperes law. So here we have a current carrying wire. So infinite current carrying wire, infinite straight current carrying wire, having circular cross section, of radius r, and current flowing through this wire is equal to I. Okay, so to find so you have to find the magnetic field at distance r, small r, from axis of the wire, if there will be two cases, when the small r is less than capital R, and second case is small r is greater than capital R, and it's given that the current density is uniform. The current density is uniform. That means if this is the current carrying wire, so this is the current which flows uniformly throughout the circular cross section of radius r. So this is the current carrying wire. This is how the current flows. Okay, and this is the axis of the wire. So we have to find the magnetic field at a distance r from the axis. That means we have two cases. R less than capital R, that is small r less than capital R, means we have to find magnetic field inside the wire. That is case 1. And case 2, small r greater than capital R. That means you have to find magnetic field outside the current carrying wire. Okay, so first we'll go for case 1. So in case 1, r less than capital R. So this is the current carrying wire. This is the current. Now say at some distance small r from this axis, you have to find the magnetic field. Obviously from symmetry you know that this magnetic field will be in this direction, right? So it will be like this now, forming this circular line. So this will be the direction of magnetic field, tangent to the circle of radius small r. So let this be B. And so we have constructed this loop, this closed loop. We can consider the closed loop at the flat surface, and the current flowing through the loop is this, right? So consider this J as the current density. J current density. Now J is equal to I, that total current, divided by pi capital R square. Okay. Now for this Amperian loop, this is the little dl. So little dl is there, and B dot dl is simply B multiplied by dl, because you have 0 degree angle between these. Okay, all throughout this dls. Okay, so integral of B dot dl is simply B multiplied by 2 pi r is equal to mu 0 into, so the current inside, the current crossing the loop is equal to J multiplied by pi. Sorry, this is smaller, right? We are considering this loop. Please correct it. So B into 2 pi small r, because this is the loop, right, is equal to mu naught J pi r square, because we consider only this much area. So therefore from here B equal to mu naught Jr by 2. In vector form you can also write like this: mu naught by 2 J cross R. See, it works. Mu naught by 2 J cross R. See, J, what is the direction of J? J is this dot, and this is the direction of R. So J cross R, here J cross R is in this direction. At all points you can check out. Say this point you can check out. So this is the vector r, and j is obviously here. It is out of the plane of the paper, so j cross r is this way. So this is a complete expression for finding magnetic field at a point inside. Mu naught by 2 j cross r, and its magnitude is actually this, mu naught jr by 2. Okay, now let's go outside this wire. So case 2, r is greater than capital R. This is the axis, this is the current flowing through the wire, and you need to find out magnetic field at this position. So draw this R. So from symmetry you know again that it will form these circular lines, and hence this is little dl, and that's this one is your loop, right? This whole thing is your loop. This flat, I mean this is your flat surface, and the loop is this one. The circumference of the open surface is the loop. So the loop has circumference 2 pi smaller. Okay. So integration of, we'll apply Amperes law. Integral of B dot dl is equal to mu naught into I. Now that's B into 2 pi smaller equal to mu naught into, see this is there the whole current will count, right? Because see, if you have this large radius smaller, right, the smaller is greater than capital R, however large it may be, even whatever radius, for all radii are greater than capital R, you have to count the whole current, that is capital I. So this B equal to mu naught capital I by 2 pi R. So this is pretty much like for outside point, it's like the field near a long wire. So if I draw the curve of B versus, let's draw the wire first. This is the cross section of the wire, current flowing this way, dot, and this is B versus R. Yes. So here from the center to this point it varies linearly, and then it's a rectangular hyperbola, right? See this part of the curve and this part of the curve. This part of the curve, the equation is mu naught jr by 2, and this part of the curve, the equation is mu naught I by 2 pi r. So here it is directly proportional to r, here it is proportional to 1 by r, 1 upon r, or inversely proportional to r. So this is a straight line and this is a rectangular hyperbola. So okay, so this was our Amperes law application number 5. Okay, so we will do one more application here. Here infinitely long wire of circular cross section, has a cavity, has a long cylindrical cavity, inside it, right? Now the axis of the cavity is parallel to axis of the wire. Axis of the cavity is parallel to axis of the wire, and J is the current density, is given. J is the current density, and it is given also that A is the distance between the axis, distance between axis of the wire and the cavity. Now thing is, you have to prove that at all points inside cavity, magnetic field is uniform, and find its value. So please read the question properly. Infinitely long wire of circular cross section has a long cylindrical cavity. Inside it, axis of the cavity is parallel to axis of the wire. So the thing is like this. Without the cavity, the wire would be like this, but the sad thing is there is a cavity here, and these two axes we are looking from here. So the axis will look like dot. So between the axis of the cavity and the wire, this is the distance A, and this is how the current is flowing. Yeah, that's it. So the current density is given as J. Too much. Right. So you have to find prove that, say, at any general point, suppose a point P inside the cavity, the field is uniform. That means at point P, this point, and all points inside the cavity, the field is same, and you have to find its value. So let's start with a fresh diagram, and we all know in this type of situations we will apply the principle of superposition. So just a representation by the diagram will show what principle of superposition is all about in this case. This one, and this is having a cavity here. Okay. Now, by principle of superposition, this thing is equivalent to having this wire plus, that is the whole idea and the whole plan of superposition, applying superposition, that it's this, the wire with the cavity can be split up into two wires. How the two wires are here, I'll show you. There it is. This is the current, this is the direction of current, and this is the cavity, so there's nothing inside, right? No current inside. Now this is equivalent to having this wire devoid of the cavity, that there's no cavity, so you have this large cross section wire only, and plus this for this small cross section wire will have current flowing this way. Now if you superimpose this, now provided they have the same current density, right? So here you have current density J, here it's J separately, and this is also, I mean, magnitude wise it's J. So suppose you have a point P here, and this is a position vector R1, and from this cavity the position vector is R2, and the position vector is A. Now for the same point, this position vector will be R1, and from here, center of this cavity, this position vector will be R2. Is the diagram clear? If it's not clear, then I have to draw one more. I think it's okay. Okay. Right. So at P the magnetic field B is the magnetic field due to this wire plus vector sum of magnetic field due to this wire carrying current this way. So you know by the formula obtained in the last problem, inside mu naught by 2, that is J cross R1, right, and plus mu naught by 2 see this is due to this one, right. So instead of J you have to write here minus J cross R2. Why minus J? Because the current density is there, so that current is flowing this way inside this small cylinder. In place of the cavity, current is flowing into the plane of the paper. So this is the term for this one, and this is the term for this one. So what you get here finally, B is equal to mu naught by 2 J cross R1 minus R2. See, R1 minus R2 is actually A, vector A, right? See, here you can apply triangle law of vector. See, A plus R2 is equal to R1. For you, I will make a fresh diagram. Only one diagram. So we have superposed it like this. First this, the large radius cylinder with the large radius outside one, then we have superposed that small radius here, this cross. So this will negate all the field, the current inside, right? Now this was it. We have chosen a point P here, position vector with respect to the center of this large cylinder is R1, and position vector with respect to the center of this small cylinder is R2, or this cavity, whatever, R2, and this is A. So you have R1 minus R2 is equal to A, and magnetic field is mu naught by 2 into J cross A. So what will be the direction of the magnetic field here? It is in the direction of J cross A. What is J? What is the direction of J? The direction of J is here and direction of A is here. So J cross A will be J cross A will be here. So at all points inside the cavity, this is the magnetic field. This is the direction of magnetic field. It is along the direction of J cross A, parallel to J cross A. So this proves that magnetic field is uniform at all points inside the cavity, and its value happens to be mu naught JA by 2.